Good day, everyone. So our topic for this video is gas law or gas laws. So I am Dr. Erwin R. Abrencilio. So for our learning outcomes, we have the following. First, identify the various gas laws. Second is to determine the factors affecting the behavior of gases. And third, differentiate the various gas laws. Explain the steps in solving problems in gas laws and perform laboratory activity about gas laws. So for our lesson outline, these are the topics that we are going to discuss all throughout this video. First is the characteristics of gases. So we have to determine what are these characteristics in order for us to understand better the different gas laws. And then we will be proceeding to the different gas laws. These are Boyle's law, Charles' law, Gay-Lussac'slaw law, and combined gas law. And then, these are the characteristics of gases. Of course, gases expand to fill any container. So the expansion of gases are affected by temperature and as well as pressure. So there's random motion and there's no attraction to each other. So gases are also like fluids. There are only two um, fluids in the states of matter, and these are the gases and the liquids. So since they are fluid, they do not have any attraction to each other. And they also have very low densities. Because of that, they do not have volume and they occupy lots of empty, they have lots of empty space. So if you are going to compare that to the molecules of solid, liquid, and gas, solids are the one on the left side, liquid is at the center, and gases are the one on the right side. So they are moving and they have plenty of space in between the gas molecules. So because of that, because of these characteristics, no, so they exhibit different behaviors compared to the two states of matter, and these are applicable to the different gas laws. So gases can be compressed. So we all know that. So they do not have that particular volume and they have lots of empty space. So gases can also undergo diffusion and effusion across a barrier with small hole, random motions. So just like what you can see in the slide, no, so that can undergo diffusion. So that means that they are spreading from using the small hole. All right. So these are the different units of pressure. Now, in gases, what you will encounter there are the volume, the temperature, and pressure. Okay, so that's why I'm showing here to you the different units of pressure. So at standard atmospheric pressure or SAP, these are those units that you can use. No, 101.325 kilopascal. 1 kilopascal is equivalent to N over M square. And that 101.325 kilopascal is equivalent to 1 atm or 1 atmosphere, equivalent to 7060 millimeter of mercury or mmHg, or also equivalent to 760 torr or 14.7 psi or pounds per square inch. So the only thing that you have to remember here is that whenever you solve gas law problems, you make sure that the units are the same. The same for pressure. If they are not the same, then convert the other one. Same temperature, same units, that is in Kelvin, and same in volume. So we also have what we call as standard temperature and pressure. So along the different gas laws, you might encounter the acronym STP. So STP stands for Standard Temperature and Pressure. So there, since it is a standard, so there are these standard temperature and pressure. So if it is for temperature, it is 0 degrees Celsius or 273 Kelvin or 1 atm or 101.325 kilopascal. So uh, if you will be using the STP, so these are the different units, no, and values that you can use. So for temperature, it is always the absolute temperature or the Kelvin scale when working with gases. So this is actually it is 273.15, but in this particular examples, we can use 273 instead of 273.15. So if it is absolute zero, it is negative 273 degrees Celsius. Okay, so I'm sure that you are familiar with the conversion of units for temperature. So let us now proceed to gas laws. So the first law that we're going to tackle is the Boyle's law. So I have here the picture of the syringe, and imagine now that you are going to hold the other end. So it is a syringe without a needle, and then you have to push it. So what will happen to the volume of the uh, syringe or the volume of the gas inside the syringe? So what happens to the pressure the gas is exerting on the syringe? So this example is a very good example of Boyle's law. All right, so let us look into the inside part of the syringe. So decreasing volume increases collisions and increases pressure. So when you decrease the volume, which is happening here on the right side, so you have to increase the pressure. So when you push the syringe here, so you have increased the pressure, and then you have decreased the volume. Since there are a lot of spaces between the gases, so they can easily be compressed. So for the first scenario, you have here the volume, which is 1.0 liter, wherein the pressure is just 100 millimeter of mercury. The other hand, on the right side, when you apply the pressure, um, twice the pressure of the first one, now it is 200 millimeter of mercury, then what happened to the volume is that it became zero point 0.5 liter. So this is an example of Boyle's law. So the pressure and volume of a gas are inversely proportional, meaning if the other one is increasing, the other one is decreasing, and vice versa, assuming that there is a constant mass and temperature. So that's why the graph here said that as you um, increase the pressure, no, you will also you are decreasing the volume of the no, not this one, not on the right side. So there's something wrong here on the right. Ah, yeah, because the label here is inverse pressure. Sorry for that. So on the left side is the pressure and the volume, and that is inversely proportional. So that you will not be confused, because the label here on the right side, it is inverse pressure. So in this case, I just want you to look on the left side of the slide showing that there is, when you say that there is inversely proportional relationship between pressure and volume, the graph looks like this one, okay? So Boyle's law leads to the mathematical expression assuming temperature is constant. P1 times V1 is equal to P2 times V2. So P1, P2 represents the final or and the initial pressure. So P1 is the initial, P2 is the final. V1 and V2, initial and final volume. So V1 is the initial, V2 is the final volume. So let us apply the formula to a certain Boyle's law problem. A balloon contains 30 liter of helium gas at 103 kilopascal. What is the volume of the helium when the balloon rises an altitude where the pressure is only 25 kilopascal, assuming that the temperature remains constant? So there are certain steps that you have to remember in order for you to solve problems in gas law. So first is you have to analyze. Of course, this is very basic. You have to analyze, you have to list the known and the unknown. So for the known, based on the problem, we have P1, 103 kilopascal, V2, 30 liter, and P2 is 25 kilopascal. So you're looking for the final volume in liters. So you can deduce it from the formula of Boyle's law, which is P1 times V1 is equal to V2 times V2. So you have to solve the unknown, which is V2. So start with Boyle's law formula. Then after that, you have to isolate the V2 by dividing both sides by P2 so that you can be able to cancel out P2, and the one that will remain is V2. So V2 is equal to P1 times V1 times P1 over P2. And then after that is you have to substitute the values for P1, V1, and P2 using the given equation. So it is 30.0 liter times 103 kilopascal over 25 kilopascal. So you can cancel kilopascal since one is a numerator and the other is a denominator. And with that, you can be able to compute it as 1.24 times 10 to the second power liters. Okay, but you may not convert it to scientific notation if you wish not to. Okay, so third is you have to evaluate. So does the result make sense? So we said that as we increase the pressure, there is a decrease in the volume. So a decrease in the pressure at constant temperature must correspond to a proportional increase in volume and vice versa. So the calculated results agrees with both kinetic theory and the pressure-volume relationship. So the units have canceled correctly. So again, one thing that you can look into also is the cancellation of units. Okay, so let us now proceed to the second law, which is Charles' law. So imagine that you put a balloon filled with gas in a liquid nitrogen. What is happening to the temperature of the gas in the balloon? And what will happen to the volume of the balloon? So as you can see on the illustration, so after putting the balloon inside the after filling it with liquid nitrogen, then what will happen? What happened to the size of the balloon? No, so from a bigger balloon, it shrunk into that, no, into that form. So because of the low in temperature. So the volume and absolute temperature of a gas are directly proportional to each other. So that means an increase in temperature leads to an increase in volume. In this case, the one that is constant is, of course, the mass and the pressure. So as you can see here on the illustration, you have here the as the volume increases, the temperature increases too when it comes with the gas. So that is according to Charles' law. So you can see here an illustration, no, of a gas that is being heated. So you have here volume 1 and then volume 2. So as you have increased here the temperature, no, mas malaking apoy niya, tumaas in temperature, there is also increase in volume. So you are being asked here, explain how the picture above shows Charles' law and what are some examples of Charles' law that you can think of. Okay, so just like, for example, tires, balloons, basketballs, footballs, and volleyballs, and others. Okay, so this is a good example in the practical application of this, no? So during summer season, the tire of a car, yung gulong ng sasakyan, no, ay hindi dapat punong-puno ng ng hangin dahil the volume of the gas inside, no, may increase due to the increase in the temperature of the tire. Since summer, mainit ang kalsada, pag umikot ng umikot yung gulong plus the friction, then iinit din yung gas inside. So pag masyadong siksik, wala nang hindi na expand pa yung gas dahil nga punong-puno na. So the tendency is to crack the the tire, and then yun, sasabog na yung gulong ng sasakyan. In the same manner naman, kapag naman malamig ang panahon, no, yung mga basketball, yung mga bola, mga volleyball na hindi ginagamit, even yung mga sasakyan na hindi ginagamit masyado, since malamig yung panahon, the tendency of the volume is to go down. So parang, kaya pag chinek mo, bakit parang malambot, no? Bakit mukha siyang flat? It is because hindi nga siya kasi dahil nga malamig, so bumaba yung volume ng gas doon sa loob. So for the formula, you have here V1 over T1, V2 over T2, but it can be expressed also as V1 times T2 is equal to V2 times T1. So let us apply. So a balloon inflated in a room at 24 degrees Celsius has volume of 4.0 liter. So the balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? Then again, the first step is to write the known and the unknown. So the known is V1, 4 liter, T1, 24 degrees Celsius, T2, 58 degrees Celsius. Unknown is again V2. Of course, since the temperature is not in a Kelvin, so you have to convert it first to Kelvin. And then you have to apply the formula. So with that, multiply both sides by T2 in order for you to cancel out T2 from the V1, from the V2. So with that, you can have a formula of V2 is equal to V1 times T2 over T1. So after that is you have to substitute using the values in the first step. So that is 4.0 liter times 31 Kelvin over 297 Kelvin is equal to 4.46 liters. So that is the volume 2. And then you have to analyze you have to evaluate the result. So the volume increases as temperature increases. So since there is increase in temperature, expect that the volume will also increase. So that is the Charles' law. And then let us now proceed to Gay-Lussac'slaw law. So imagine you have a balloon inside a container that ensures it has a fixed volume. And then you heat the balloon. So what is happening to the temperature of the gas inside the balloon? What will happen to the pressure the gas is exerting on the balloon? Okay, so according to Gay-Lussac, so the pressure and absolute temperature of a gas are directly proportional. As temperature rises, so does pressure. So pag tumaas ang temperature, tataas din ang pressure. So a good example of this is of course, even in the tire, it's also applicable. A good example of this is aerosol spray, no? So yung mga empty can ng mga aerosol spray, yung mga pabango natin dyan na binibili sa mga mall, na pag in-spray mo, natunog na, that's aerosol. So, kaya may nakalagay doon sa likod, bawal mo siyang ilagay sa malapit sa apoy or pag wala ng laman, bawal mo siyang sunugin. Okay? So, because if you will do that, there will be an increase in temperature. So, yung pressure sa loob, tataas din. So, tendency, sasabog yung canister. Okay? So, with that, we have this formula. P1 over T1 is equal to P2 over T2, or P1 times T2 is equal to P2 times T1. So this is an application of that for problem solving. Aerosol cans carry labels warning not to incinerate or burn the cans. Ito yung binabagit ko sa inyo kanina sa bawal sunugin. This problem will show why it is dangerous to dispose of aerosol cans in a fire. The gas in use aerosol can is at a pressure of 103 kilopascal at 25 degrees Celsius. If the can is thrown on a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? Correct. So again, a formula, list the known and the unknown. In this case, the unknown is the P2 or the per kilopascal. So solve for the unknown. Remember, because this problem involves temperature and gas law, so you have to convert degrees Celsius to Kelvin. And then calculate for the unknown using the formula. Multiply both by T2 on the right side and left side so that you can be able to cancel out T2 from P2. And with that, you have a formula of P2 is equal to P1 times T2 over T1. Then substitute the formula. So you have here 4.15 times 10 to the positive 2 kilopascal or 415 kilopascal. And then evaluate. So expect that there is an increase in temperature of a gas to produce an increase in pressure if the volume remains constant. So with that, let us continue with combined gas law. Okay, so in the combined gas law, it is the combination of the Boyle'slaw, Charles law, and Gay-Lussac'slaw. So with that, you have an equation of P1 V1 over T1 is equal to P2 V2 over T2, or P1 V1 times T2 P2 V2 times T1. Okay, so let us use this problem solving in order for us to understand it better. So the volume of a gas filled balloon is 30.0 liter at 313 Kelvin and 153 kilopascal pressure. What would the volume be at standard temperature and pressure? So it is STP. So a while ago, at the beginning of the video, I told you the value for STP. So write the unknown. So V1 is 30 liter, T2 is 313 Kelvin, P1 is 153 kilopascal. Now, the T2 and P2 is the STP, standard temperature and pressure. So standard temperature is 273 Kelvin. And for the standard pressure, we use the kilopascal since the given is kilopascal. So that is 101.3 kilopascal. So the one that is unknown is V2. And then you have to state the combined gas law. And then you have to isolate P2. So that means you have to isolate V2, not P2. Isolate V2 by multiplying both sides by T2. And then after that is you have your formula of V2 is equal to V1 times P1 times T2 is equal over P2 times T1. So after that is you have to substitute the unknown quantities to the equation and solve. So you'll have an answer of 39.5 liters. Then after that is you have to evaluate. So a decrease in temperature and a decrease in pressure have opposite effects on the volume. So the result is 39.5 liter. So for your activity 7, I want you to answer the following questions. You have 5 questions here. You have to follow also the different steps that I told you to that will help you in solving these problems. So with that, thank you so much for listening to this video. So these are the references for the complete details. And then, thank you so much.